Welcome back. In this video, I'm going to be discussing a topic determining relation between two variables. That's the chapter 4 of the book we are using. And here are the topics I'm going to cover under this. The first is going to be scatter diagrams, correlation, least square regression. In this video, if I can cover contingency tables and association, I will. Otherwise, that will be on a separate video. So let me recall some of the terminologies that we've seen in the previous videos. The response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. Okay. Univariate data in which a single variable is measured for each individual in the study. That's what we call univariate data. Okay. For example, the total rainfall in Potsdam, New York, recorded every year for 5 years. That would be a univariate data. All right, so when we talk about bivariate data, we mean the data in which two variables are measured on an individual. So just two. For example, if we collect data on students in a particular start class, where the data is the number of days of mixed classes between exams and exam scores. So we are looking at a particular student and we're comparing how many days he has missed the class compared to the score he or she gets in the exam. So we say this is a bivariate data after collecting such. All right, so let's go into scatter diagram. This is a graph that shows relationship between two quantitative variables. I want you to take notes. So this is two quantitative variables measuring this on the same individual. All right. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal and the response variable is plotted on the vertical. So we have a graph that looks this way. And the horizontal is the explanatory variable. And this will be response variable. Okay. All right. What are various types of relations in a scatter diagram? We have linear. Okay. We have linear could be this direction or this direction. We have nonlinear. And these are all nonlinear. C and D are nonlinear. And then he is no relation. I want you to take note of some of these. The shapes of these graphs. Okay, so we are going to deal with this very shortly. But let's look at some example on scatter diagrams. Because of the way it is, I'm not going to dwell on how to plot the graph. I'm going to show you the graph, but on a separate video, I'm planning to use Excel or StatCrunch to do all this analysis, which is very, very easy. You can easily plot a scatter diagram in Excel. for example. All right, so the data shown to the right are based on a study for drilling rock. The researcher wanted to determine whether the time it takes to drill a distance of 5 feet in rock increases with the depth at which the drilling begins, okay? So when you start to drill, how do you relate the distance and the time it takes to drill? Okay. So depth at which drilling begins is the explanatory variable, that is X in this case, and time to drill 5 feet is the response variable, that is Y. So what we need to do is to draw a scatter diagram of the data. And if you use Excel, that will give you something like this. So this is the way scatter diagram looks like. The first point here correlates to when X is 35, the time is 5.88 minutes. So that's why we have something that is close to 35 all the way to something that is close to 6. Okay, this is not starting from 0. So that is very obvious because this is 50 to 100. So, and this gap is not as wide as this. So we don't expect this to be. And that's the power of scatter diagram. You don't have to start from 0. All right, so that's each of these points represents the data. X correlates X with Y. All right, so more definitions in terms of correlation. 2 variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable. And the same thing, below average values of one variable are associated with below average of values of the other variable. In a very simple way, in a very simple one, let's say we have 2 variables are positively associated, okay? That's why I put this in red. Whenever the value of one variable increases, the value of the other variable increases. That's a very simple way to put positively associated variables. All right, so let's look at negatively associated variable. When above average value of one variable are associated with below average value of the other variable. And just to put it in a simple form also, we say whenever the value of one variable increases, the value of the other variable decreases. That's what we mean by negatively associated. All right. Remember, positive means one variable is increasing, the other variable is also increasing. Negative means one variable is increasing, the other is decreasing. Or one variable is decreasing, the other is increasing. All right. One major thing we are going to be using is what we call linear correlation coefficients. Our focus actually is about linear correlation. So we want to see if there is linear correlation between 2 variables. And this guy called linear correlation coefficient, this R, is going to give us a lot of information about the variable X and variable Y. The response variable X and the explanatory variable Y. All right, so here is the formula. We find the mean for each of the variable, and then we subtract every data point from that. We divide by the standard deviation of each of the variable, and then sum the multiplication and divide by n-1. Again, I'm going to make a separate video that you can easily compute this in Excel or StatCrunch very easily without going through this. Of course, I'm going to show an example here very briefly. Before then, let's look at the properties. What can this linear correlation coefficient R, what can it tell us? What can we infer from the value? First, the linear correlation coefficient is always between -1 and 1. If you're doing some calculations and you get something that is outside this range, something is wrong. Of course, it could be -1 and it could be 1, and any number in between. That's the first property. Secondly, when you have R to be exactly 1, we have what we call a perfect positive linear relation. Okay, a perfect positive linear relation when n is +1. When n is exactly -1, I'm talking of the extreme right now, the extreme left now, then we have a perfect negative linear relation. So +1, perfect positive linear relation, -1, perfect negative linear relations. Another property is that the closer you are to +1, the stronger the evidence that the evidence is of a positive association. The stronger the evidence. And so we are going to check. All right. And the closer you are to -1, the stronger the evidence is of a negative association. If R is close to 0, so we move to the right, +1, we move to the left, -1, and then what happens if we come in the middle? It happens that as close as R get close to 1, there is little or no evidence that there is a linear relation between the two variables. Now, the one I want to make here is that does not mean that there is no relation. R close to 0 does not imply no relation. We are only saying that there is no linear relation, okay? Because the focus here is the linear relation. So there could be other type of relation, non-linear. And maybe there is no relation. But for us, R close to 0 means there is no linear relation. Please take note of that. Number 7, the properties of this linear correlation coefficient R. The linear correlation coefficient is a unitless measure of association. So it doesn't matter what's the unit of X and Y. R is unitless, so we don't have to consider those. And lastly, correlation coefficient is not resistant, okay? Is not resistant. When you add extreme values, the statistics you get responds very, very well. So if it is resistance, even when we had extreme values, the value of the statistics will not change so much. I discussed this in my previous video. For this linear correlation coefficient, it is not resistance. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. This is very, very important. Okay, so picture-wise, of course, it's nice to see the graph so that it makes it more visualized and people can easily remember. So when I talk about perfect positive, you can see that the point lined up. This is not something you see most of the time. All right. Increasing, increasing. X is increasing, Y is increasing. That's what we mean by positive linear relation. And so if you scatter like this, we say it is strongly positive linear relation. And you can see that the R is very close to 1. And more scattered means moderate, R very close to 0.4, for example. And the other one is also -1 for negative linear relation, close to -1, also strongly negative, moderate, And when there is no relation, we can see when R is close to 1 and there is no relation, it can be all over the place. When R is close to 1 and you have non-linear, in this case, there is relation, but it's non-linear. You have something like this. So when you know this picture, each time you are doing some analysis and you draw your scatter diagram, you can be able to tell what is the relation between the two variables you are considering. All right, so let's look at an example. Determine the linear correlation coefficient of the drilling data. This, of course, I wouldn't want to go through finding standard deviation for the two variables and the mean. I've talked about that in my previous video. Please take a look at those videos if you miss any of them. All right, ideally, this is what you have. You are going to have the table set up this way. I'm going again, do a separate video where these things are calculated directly in Excel, Microsoft Excel or StatCrunch. Okay, so be very, very careful with this. Of course, it's not difficult once you know the mean for each variable. This is the mean here for X. This is the mean here for Y. And this is the standard deviation for X. This is the standard deviation for Y. And we make the table. So X35 minus the bar 126 divided by 52.2284. That's what you get this from. And once I do that for all the points here, all the observations, both X and Y, then I multiply these two results. So I multiply this one with this one. And that's where I get this from. And at the end of the day, I sum up all this. That's where I get this from. So the correlation coefficient is the sum of everything, which is what we have here. So that is 8.501037. And then divide by n here is how many are the observations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 observations, so I have 12 minus 1. So invariably, this is 8.501037 divided by 11. And what I get after that, if you use your calculator, you are going to get, so we have 8.501037 divided by 11. So we have 0.773. That is the correlation coefficient. Okay, and again, this can easily be obtained using Excel. All right, how do we test for linear relation? Once you get the value, remember that there is strong evidence does not mean exactly the word. So how do we test it? First step, determine the absolute value of the correlation coefficient. Means that you find if it's negative, you put the absolute value. All right, so find the critical value in table 2. I'm going to show you the table very soon, and that is everywhere. You can easily get that on the internet. A critical value table. If the absolute value of the correlation coefficient is greater than the critical value, we say a linear relation exists between the two variables. Otherwise, no linear relation exists. Again, all we claim here is that no linear relation exists. We do not say that there is no relation between them. Okay. So here is the critical value for the correlation coefficient. Remember that ours, the N for that example we just did is 12. So critical value is 0.576. I'm going to use this in the next slide. All right, so for the same example, determine whether a linear relation exists between time to drill 5 feet and depth at which drilling begins. Remember that what we got was 0.773. Is closer to +1, so we might be having a strong evidence, but let's actually determine what type of relation. Good. So let's look at this. Okay, the correlation between drilling depth and time to drill is 0.773. That's what we got before. The critical value, again, I just showed you in the previous slide, it is 0.576. So clearly, if we follow the steps, the correlation coefficient is bigger than the critical value. So there is a positive linear relation between time to drill, 5 feet, and the depth at which drilling began. Okay. We have some strong evidence to say that, but this is really the way to ascertain that. All right, now there is this very crucial thing I have to mention here: correlation versus causation. So according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Okay, should we now say this is a very high correlation coefficient? It's very close to 1, so there's a strong evidence that there exists a positive linear correlation. All right, but does this mean that a higher percentage of female with bachelor's degree causes a higher percentage of births to a married mother because they have a very strong correlation? Certainly not. Okay, certainly not. We know that these two things have nothing in common. The correlation exists only because both percentages have been increasing since 1990. The percentage of those who are getting bachelor degree is increasing. The percentage of the other one for the unmarried female is increasing. And that is why we get a very high correlation coefficient value. It is the relation that causes the high correlation, okay? In general, time series data may have high correlation because each variable is moving in a specific direction over time. So that does not mean that one is causing the other, okay? There are situations where something is causing the other, as causation, but correlation doesn't have to be causation. When data are observational, this is the key, we cannot claim a causal relation. A causal relation exists between two variables. So when we are talking of observational data, we can, whatever we get is not sufficient to say that there is a causal relation. However, when the data are collected through what we call design experiment, I discussed this in the first chapter, then we can claim causality. So this is a very serious, it's something that students have to pay closer attention. Correlation is different from causation. And I think these last 2 points distinguish the two. One, observational data, you cannot claim causation. Design experiments will give you causality. So another way that two variables can be related even though there is not a causal relation is through a locking variable. I discussed what locking variable is in my previous video, just look through. So a locking variable is related to both the explanatory and the response variable. For example, okay, this is a very good example. Ice cream sales and crime rates have a very high correlation. Does this mean that local governments should shut down all ice cream shops? Because if ice cream sales and crime rates have very high correlation, 0.9 something, should we now say, oh, shut down all the ice cream? Maybe that will make the crime rate to come down. Certainly not. The locking variable here is the temperature. As here temperatures rise, both ice cream sales and crime rates increase. All right. Now, I want to go into the next section, least square regression. Again, I'm going to present some videos that we talked about how to do all this in Excel and or a StatCrunch. Here, the goal is to find a linear equation that fits this data that can be used to give expected value of the response variable for a given explanatory variable value. So the goal is to look at the linear equation since we were talking about linear correlation. So before we go into least square proper, when we deal with this in basic math, college algebra, I give you some data, X and Y. And the goal here is to find a linear equation. Find a linear equation. How do you find a linear equation? Get the 2 points, any of the 2 points you want here, and then find the slope. Then use that to find the equation of line, the graph equation on the scatter diagram. So this point can be plotted as scattered diagram. We can come out with the equation. So I'll briefly go into that. And of course, we can predict when y, we can predict the value of y when x is 3. All right, so very quickly, let me find the equation. So you can choose any point you like. I would just like to work with 2 and 5.7. Then I would like to work with 6 and 1.9. So let me say I have 2, 5.7, that's the first point, and then 6, 1.9, that's the second point. Remember, so let's call this x1, y1, x2, y2. Slope first, the slope of these 2 points, the slope using these 2 points will be y1 minus y2 over x1 minus x2. So that would be 5.7 minus 1.9 divided by 2 minus 6. And that should give us minus 0.95. All right. And once you find the slope, you can find the equation of line using any of the points. So that would be y minus y1, if you desire to use the first point, equals the slope times x minus x1. And so plug in y1 and x1 and the slope. So you have y minus, what is y1 here? y1 is 5.7. y1 is 5.7, so I have 5.7. Here, the slope, we got that to be minus 0.95. And we have x minus x1 is 2. Now, if you move things around, you have y minus 5.7 equals minus 0.95x plus what you get here is 1.9. All right, so I can now move this guy to the other side, and finally I will get y equals minus 0.95x plus 7.6. So this is the equation of line that we pass through the 2 points. Okay, this is the equation of line that will pass through the 2 points. And of course, from the basic math, this is the slope. Slope is minus 0.95, and the y-intercept will be 0.7.6. All right, that is what we want to see first. So when we have this equation, we can graph it. Again, you can do this easily with Excel. I'm just going to walk through it and show you the graph straight away. So when you plot this point, scatter diagram, you have all these points, and this is the equation. Now, our goal here is not just to draw any line, because you remember I chose the first and the fifth point. What happens if somebody choose the first and the second point? You get another equation. You get something like this. You get another line. You get different lines. The question is, can we find the best line in a way that the data point will be as closer as possible to the line? And that is what least square regression is. For us, okay, if we want to use that to predict, so I'm going to have y. Remember, the equation we got was y equals minus 0.95 times x plus 7.6. So when x is 3, we have y equals to minus 0.95 times 3 plus 7.6. Use your calculator. What you get is 4.75. All right. And that's all we need to do in this. So let's move on to what is called residual, okay? The difference between the observed value of y and the predicted value of y is the error, or what we call residual. And we can quickly check, okay? Because for least square, we want the residual to be minimal. The line with minimal residual, that is what least square regression line will give us. So for the previous example, for the example we are dealing with, residual, we can easily compute it. Remember that when x is 3, we know the value, okay? It's 5.2. So the actual value, the observed value is 5.2, but what we got in the previous slide is 4.75. So when we subtract the 2, we have what we call the residual, which is 0.45 in this case. And picture from the graph, you can easily see. So the particular point corresponding to 5.2 is this guy, and this is the value we got. And the difference here, the gap between this point and this vertical line difference is the residual. So how do we make sure that this gap, there is the line we have is such a way that these 2 points are very close, and every other point the same vertical line distance? So let's now talk about what least square regression criterion is. So least square regression line is the line that minimizes the sum of the square error or the residuals. Okay, this line minimizes the sum of the square vertical distance. Like I've said before, it's the vertical distance between the observed values of y and those predicted by line. We call it y hat, okay? So that to differentiate it from the observed value. So minimize sum of the residual square. And we do that because the distance we want it to be positive. All right, so the equation of least square regression line is given by this, okay? Y height equals to B1x plus B0. What is B1? B1 is R, which is the correlation coefficient, times the standard deviation corresponding to y over the standard deviation corresponding to x. And of course, the way this is written, B1 is the slope of the least square regression line. And of course, B naught is y bar. Y bar is the mean of y minus B1 x bar. X bar is the mean of x. Okay, and B1 is what we got before to be slope. So invariably, we need to find B1 first before finding B naught, and then plug everything into y hat to get the least square regression line. Okay, so B naught in this case is the y-intercept. I just spoke about all this. All right, so let's go back to the same example. Find the least square regression line, okay? That's the first question. Predict the drilling time if drilling starts at 130 feet. Is the observed drilling time at 130 feet above or below average? Draw the least square regression line on the scattered diagram of the data. So let's answer them one by one. Now, I don't want to bug you with finding the mean and the standard deviation for each variable. We can do that by using Excel, and we have the value before. So these are the values. And remember that we found the correlation coefficient also to be 0.773. So let's compute what the B1 will be. Remember that R is 0.773 times XY is 0.780774 divides X, standard deviation for X is 52.22874. And if you use your calculator to do this, all you get is 0.0116. All right, so just to repeat the answer we just got in the previous slide, we have 0.0116. Now for B naught, Y bar, the mean for Y is 6.985833 minus the B1 we got is 0.0116 times X bar is 126.25. And if you do that multiplication with your calculator, what you will get here is 5.5213. All right, so we have B1 and we have B naught. We can get the equation of linear least square regression line now to be B1 is 0.0116 plus, times X plus 5.5213. That becomes the equation of the least square regression line. So this one is better than just picking any arbitrary point. So we want to use this to predict drilling time if drilling starts at 130 feet. So all we do here is to substitute 130 for X. So I'm going to have 0.0116 times 130 plus 5.5213. And if you use your calculator very well here, you will get 7.0293. Okay. The observed drilling time is 6.93 for 130 feet. So if I have 130 feet here to my right here, the observed drilling time is 6.93. All right, but what we got in the predicted one is 7.0293. Therefore, the drilling time of 6.93 seconds is below the average. And if you plot that line for this, you'll get this relation. this will be the best line fit. Now let's interpret the slope and the y-intercept. All right, so the slope of the regression line is 0.0116. So what is this interpretation? For each additional foot of depth we start drilling, the time to drill 5 feet increases by 0.116 minutes on average. That's what happened. Now, if we had gotten the slope to be negative, then that means the time to drill 5 feet decreases, okay? That would be the difference. Now, what's the interpretation for the intercept? Okay, this is very tricky. Y-intercept of the regression line is 5.5273. How do we interpret it? We need to ask 2 questions, very important. Is 0 a reasonable value for the explanatory variable? Can we really have y to be 0? Do any observations near x equal to 0 exist in the data set? So once we answer these 2 questions, it makes sense to have y-intercept because x has to be 0 to get y when we talk about y-intercept. First, a value of 0 is reasonable for the drilling data. Why? The drilling can start on the surface of the head. That will make it to be 0. The smallest observation in the data set, if you observe the table, that is 35 feet. So it's reasonable close to 0. So interpretation of y-intercept here is reasonable. If these 2 questions are known, if we cannot answer these 2 questions, it means that interpretation of y-intercept is not reasonable. So the time to drill 5 feet when we begin drilling at the surface of the head is 5.5273 minutes. That's what the intercept with. At the surface of the head, we have not gone any feet deep, so x is 0. We can get the intercept. All right. So very quickly, before I round up this section, I want to talk about a caution. If the least square regression line is used to make prediction based on the values of the explanatory variable that are much larger or much smaller than the observed value, we say the researcher is working outside the scope of the model. Be extremely careful because we talked about this before in my previous slide. This is not resistant. So we have to never use a least square regression line to make prediction outside the scope of the model because we can't be sure the linear relation continue to exist. The linear relation may not continue to exist. So it has to be within the scope because this is not resistant. I will stop the video here. And in my next video, I'm going to talk about contingency tables and association, which is very, very important and widely used. See you in my next video. Thank you very much. Don't forget to leave any comments. If you have any questions, I'm available to answer you. Just leave a comment. Thank you and see you in my next video.